Okay, so now let's look at the E2 reaction. The mechanism for the E2 reaction is as thus. It's going to be akin to our SN2 reaction in that everything is concerted in one movement. You'll see that the base abstracts the proton. So we don't have removal of the leaving group first. The base is going to abstract the proton, which then spurs the removal of our leaving group. These are going to occur in a concerted fashion. And for this reason, it is a second order reaction. That's because it's dependent both on the amount of base that is present and the amount of starting reactant that is present. Both of these are key for the main and only step of the reaction. So this is a second order reaction. I also want to note something. We're going to talk about this in more detail, but because this is a concerted reaction, note that the hydrogen that is abstracted and the leaving group, in this case bromine, are oriented 180 degrees from each other. That's an anti, and we'll talk more about that. This is kind of like having to have a backside attack in our SN2. Similarly, the hydrogen that's removed and the leaving group have to be opposite of each other. You have this attack from the base that is coming from essentially the back, and then the removal of our leaving group from the opposite side. As stated, E2 is a second order reaction. So our rate law is going to be dependent on both the concentration of the starting substrate and the base that is added for the reaction. So any amount of increase in concentration from the reactant or from the base will increase the rate of the reaction. Now, I talked about stereochemistry being something that affects one of our two reactions, and that is the E2 reaction. I'll actually go back to the slide to remind you. When I was talking about the different reactions, I noted that one of our reactions is sensitive to stereochemistry. That was that with certain stereochemistry, we actually saw that it didn't follow Zaitsev's rule. And the reason for that in an E2 reaction is because of this need to be anti when removing our proton and our leaving group also leaving. Remember, I said these have to be opposite 180 degrees from each other or anti from each other for the reaction to take place. So for example, in our top reaction here, if we treat the top alkyl halide with a strong base, this will progress an E2 type reaction. You get this non-Zaitsev product, this product that is not on the most substituted double bond. This is the product that you form. And that's when we start with this ring right here. And again, now if we make one modification, we use the same molecule and we make one modification, and that modification is the change in the positioning of this CH3 group. So now the CH3 group is down instead of up before. We do make the Zaitsev product. So we haven't changed this from a strong to a weak base. This is still a strong base, but we actually change the stereochemistry of this carbon next to the bromine. And we get the Zaitsev product instead of the non-Zaitsev product. And the reason that that changes it is because we have allowed for an anti-hydrogen in the position that would make the Zaitsev product, the major product. Again, these results suggest that the hydrogen and the leaving group have to be anti from each other. That means if one is up, the other has to be down. Or if one is shown as a wedge, the other has to be a hash. You can see it a little bit better in this type of example. This is a actual experiment using isotopically labeled products. So one of the hydrogen is replaced with a deuterium. Deuterium acts just like hydrogen. It's just a heavy isotope of hydrogen. And so we'll react in the same way, but we're able to kind of follow it and track it. So here's our starting ring here. We're going to remove this bromine. Okay, that will be our leaving group. And when forming an elimination reaction, remember we have to have a hydrogen that is on a adjacent carbon to this bromine. Now there is a methyl group here. I'm going to write it out so you know that. And there's also a hydrogen here. You would think that you form a double bond here, right? Because there's a methyl group and this is a methyl group. So you'd form a very substituted double bond. However, when we look at this product here, we see the non-Zaitsev product. And notice that the hydrogen that was abstracted is not the deuterium. Specifically, the only product takes this hydrogen. Oh, excuse me. That's for the opposite one. The product here takes the deuterium. It only takes the deuterium. Notice that the product does not have the deuterium, excuse me. And so the deuterium hydrogen was the only hydrogen that was also abstracted during the formation of our double bond. The placement of the deuterium is up, where the placement of the bromine is down. So they are anti from each other, and thus this reaction can proceed. Notice that the other hydrogen available, this hydrogen, is down, and the bromine is down. These are not anti from each other, which is why the reaction cannot proceed using this hydrogen and forming the Zaitsev product. So you instead form this non-Zaitsev product. Now when we rearrange things, again, we've rearranged to put the deuterium in the down position here. Nothing else has been changed on this ring. It's still going to form the non-Zaitsev product, but notice that this time the deuterium is present. That's because, just like last time, our bromine is going to leave with the hydrogen that is anti from it, which is the hydrogen in the up position. This time it's not the deuterium, and you can see that deuterium is left over. Again, the leaving group must be anti to the hydrogen that is being removed in order for the elimination of an E2 elimination to occur. And you can see this in a ring that's drawn this way where we use wedge and hash, or you can look at it, for example, in a cyclohexane in the chair position. Here you can see that only the orange hydrogen, when looking at the hydrogens available, is 180 degrees and anti to this bromine. And so only this hydrogen can be removed to make the double bond. Now, cyclohexane rings have a little bit of a extra condition in that in order for the reaction to have an anti-conformation, the groups also have to be axial from each other. So they still can be anti in that one is up and one is down. Remember the difference between up and down and axial and equatorial. Remember that something can be up and axial, or it could be down and axial, or vice versa. So for an elimination reaction to occur, they have to be anti, meaning one needs to be up and one needs to be down. But for rings, for cyclohexane rings, first they have to flip in a way that things are axial as well. Generally, this just means that conditions that affect if a ring is axial versus equatorial, and we've talked about how that can be affected. Remember that certain groups on a ring will shift the tendency of the ring to be in an axial versus equatorial position. Remember, these rings are usually generally flipping between axial and equatorial, back and forth, back and forth. But for example, bulky groups on a ring will affect how much it flips between axial and equatorial. And if it is less often in axial positioning, in that conformer, then it's harder for an elimination reaction to occur. And elimination reactions are slower on cyclohexane rings where you have less time spent in the axial position. But axial and equatorial, although they have to be in this position for the reaction to occur, it doesn't distinguish this rule, which is that they are anti to each other. That just means one has to be up and the other has to be down, or vice versa.